Okay, so welcome to Math 349, Operations of Order. This should be lecture 26. And what I want to talk about today is to, finish up our discussion on gaps, although there's, of course, a tremendous amount more that we can do about this. And so I'm mostly going to be talking about two papers that are listed below at the bottom of the slide, as well as a little bit on another one, the longest one of heads, which is an absolutely remarkable paper. The result is shocking. It's extremely well written. Strongly urge all of you to look at this. I think I've actually even listed this as one of the examples of excellent mathematical writing. So this is something that should have already been on your radar screen a bit. Okay, so right now we're still talking about gaps between objects. And so before we do the gaps between summons and second order decompositions, I thought we would start off with something easier. And so, as always, we try to build intuition by looking at easier problems. Sometimes, of course, there's the danger that the problem might be so easy or so much simpler than the one we care about that all the key features are not there. And there's a different mode of attack that works for that problem, but will not work in general. So let's look at, gaps in binary decompositions. So I hope everybody is familiar with binary. So in binary, we have 1, 2, 2 squared, which is 4, 2 cubed, which is 8, ... In decimal, it's 1, 2, I'm sorry, not 1, 2, 1, 10, 10 squared, which is 100, 10 cubed, which is 1,000, and so on. And we can write any number x as a sum, say k goes from 0 to n of, I'll do dk 10 to the k for a decimal, or I could write it maybe as the sum, L goes from 0 to m of BL 2 to the L for binary. And so every number has a unique decomposition base 10, it has a unique decomposition base 2. If I choose any positive integer greater than 1, there will be a unique decomposition. And then the digits here, dk is in 0 through 9, BL is in 0 through 1. So things are a lot easier in binary. If the digit's not a 0, it's a 1. And so when we write things like this, usually it's implicit that the last, the leading digit is not 0. Normally I would not write x equals 00314. I would just write x equals 314. So when I'm writing something like this, I would frequently want to write it so that the largest index corresponds to a non-zero digit. But of course, sometimes I may not want to do this. Maybe I'm enumerating all numbers that are less than or equal to a given amount, in which case I would have to allow some of the leading digits to be 0. So you just have to be a little bit careful in terms of what you're looking at. Frequently, we like to normalize numbers so that they have roughly the same size. So we don't want to compare say x, which is around 10 squared, and y, which is around 10. That. We would obviously expect it to be very different properties with numbers that differ by so many orders of magnitude. So frequently, study, say, x and y maybe in some interval 10 to the n, 10 to the n plus 1. It doesn't really matter if we take your open or closed intervals on the end. That's only going to be one more number. It's not going to make a huge difference. It's often advantageous to have it closed on the left and open on the right so that we have a sequence of disjoint intervals as we march down. Also, of course, when we write it like this, this means that the leading digit is not going to be a 0. Or, of course, we could study them in maybe the interval 2 to the m, 2 to the m plus 1. So does anybody know why? I'll see if I can hear your voices. Why it might be easier to study gaps in binary versus gaps in decimal? I also have a second computer open, so if you put something in the chat, I will hopefully see it. Does anybody have any thoughts as to why binary might be easier?
Is it because it's easier to represent it on a computer?
Well, so computers, of course, love binary, and when in doubt, talking about computing things with modern technology, that's not a bad guess. Why do computers like base 2? Let's look at two numbers. Let's look at 324, which would be 3 times 10 squared plus 2 times 10 to the first plus 4 times 10 to the 0. What are the gaps? If you think about it, can somebody tell me what are the gap lengths that we see in the number 324? Do we see a gap of length 5? Do we see a gap of length 2? What do we see?
What do you mean by like a gap between 320? Is that what you're asking?
Oh, no. When we look at the summons, so when we do a Zeckendorf decomposition, it was the space between indices. So here we have 3 times 10 squared, 1 times 10 squared, 1 times 10 squared, 1 times 10 squared, 2 times 10 to the first, 1 times 10 to the first, 1 times 10 to the first, 1 times 10 to the 0, 1 times 10 to the 0, 1 times 10 to the 0, 1 times 10 to the 0. So we have 103 times. Just writing it all out. We would have 100, 100, 100, 10, 10, 1, 1, 1, 1. These would all be the first index. These would be the second index. And these would all be the third index. So what are the gaps that we would observe? Do we ever see a gap of length 5 between indices? Between two indices, do we have like a third index and then the next one after that a eighth index? Do we ever see something like that? I need more people to speak up. You either have to say yes, no, or I'm not sure. I can't see faces.
I'm not sure.
Okay, so if we wanted to have a gap of length 5, we would have to have an index, maybe the 5th index, and then we'd have to have a 10th index. Or we'd have to have the 2nd index and the 7th index. We'd have to have 2 indices that differ by 5 with nothing between them. So do we have that here?
No.
No. Do we have anything that differs by 4 indices?
No.
So what's this? What gaps do we have?
Just one?
What size?
One?
Okay,
We don't have
so
two,
it's-
right? Because between first and third exists a second, so that means that,
correct.
okay,
So,
so the
so
gaps are
when we
only
go,
like,
so when we go from, you know, the ones to the twos, that's a gap of length 1. Right? And we have a gap of length 1 when we go from 2 to 3. Do we have any gaps of length 0? So when we have multiple copies of, say, one index, so those are our 2 gaps of length 1. Do we have any gaps of length 0? So do we have 2 copies of the same index? Is there any index that's repeated? So what's the first index that's present?
the first index
The first index. And how often do we have the first index?
4 times.
4 times. So is there a gap of length 0? Do we have 2 copies of the first index?
We have 4 copies, don't we?
So we have 4 copies. So how many times are we going to have a gap of length 0 here? When we go from the first index to the second index, that's a gap of length 1. When we go from the first index to the first index, that's a gap of length 0. How often do we go from the first index to the first index? Well, we start off with one gap of length 0, right? Then we have another gap of length 0. And then we have another length 0. So we have 3 zeros. So do you see how we have 3 gaps of length 0 from the first indices? And then the fourth one gives us the gap of length 1 when we go to the second index. What about the second index? Do we get any gaps of length 0 from that? So when we look at the second index, are there any gaps of length 0? So there should be one gap of length 0 when we go from 110 to the next. Then we have a gap of length 1 when we go from 10 to 100. And now how many gaps of length 0 do we get for the remainder of the third indices?
Two.
2. And so this would be the distribution of gaps. And notice how we have a lot of gaps of length 0 that we have to be careful about. If I give you the number, let's do 300100002. 1. Let's do it like this. So this would be 10 to the 0, 10 to the 1, 2, 3, 4, 10 to the 5th, 10 to the 8th. So we would have as summons, we would have 10 to the 8, 10 to the 8, 10 to the 8, 10 to the 5th, 10 to the 1, 10 to the 0. So these are my summons.
Shouldn't there be 2 10 to the 1s?
Oh, yes, thank you. There should be 2 10 to the 1s. Thank you. And now what would my gaps be? what's the first gap I would get? And when I start with the smallest, I start with 10 to the 0, I start with 1. Do I have multiple copies of 1?
No.
No.
No. So I'm not going to have any gaps of length 0 because I don't have multiple copies of 1. So the first gap it's going to give me is when I go from 10 to the 0 to 10 to the 1. That's going to give me a gap of length 1. I'm sorry, I'm supposed to be doing this in green. Now, when I go from, I've gone from 10 to the 0 to 10 to the 1, that's going to be a gap of length 1. What's the next gap going to be?
Like length 0.
It's going to be 0. And now, how long is the next gap?
Or
It's going to be 4. And then how long is the next gap going to be?
Three.
3. And now I'm just left with what's going on here. And I'm going to have 2 gaps of length 0. So there's my first, and there's my second. So that would be the those would be the gaps. So I would end up with 3 gaps of length 0, 1 gap of length 1, no gaps of length 2, 1 gap of length 3, 1 gap of length 4. So what makes base 10 a little bit hard is that I've got to be careful because I could have lots of gaps of length 0. It turns out it's not too bad to look at this, but it's much easier in binary. In binary, what are the only possibilities? What are the possible lengths for gaps in binary? It's almost the same as decimal. What's the only difference? So when
There's no gaps of 0.
Yep. No zeros. Only 1, 2, 3, da, da, da. That's because something in binary, we often put a subscript 2 there to remind us that this is in binary and not in decimal notation. So this means binary. Okay, so things are a little bit easier when we look at gaps of binary representations because we don't have to worry about having multiple copies of the same summand. Each summand occurs once and only once. That's very similar to the Fibonacci's. So I would say doing things base 2 is a lot more in line with the Fibonacci's. Could the following be a Zeckendorf decomposition, where 1 means I have the summand and 0 means I don't? Could this be a Zeckendorf? So can someone tell me what is a Zeckendorf decomposition? So what do we use the Zeckendorf decomposition for? What kind of numbers does the Zeckendorf decomposition involve?
Fibonacci's.
Integer Fibonacci.
Right, and so the Zeckendorf is we write our number as the sum of non-adjacent Fibonacci numbers. And each number is used once at most. Could this be a Zeckendorf decomposition, where 1 means we have the corresponding summand So this would be like F1 plus F2 plus F3 plus F5 plus F6 and so on. Could this be a Zeckendorf decomposition?
But Professor Miller, could you go over one more time what exactly determines a Zeckendorf?
Sure. So a Zeckendorf decomposition of n is, we can write n as, say, fi1 plus fi2 plus dot 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 plus fik, where never use two adjacent Fibonacci numbers. Each Fibonacci number used at most once. And we define it as f1 is 1, f2 is 2, f3 is 3, f5 is 5, and so on. And so if we do this decomposition, every number can be written uniquely as the sum of non-adjacent Fibonacci numbers. So if I gave you, say, 1, 1, 0, 1, 0, 1, 1, 1, that might mean f1 plus f2 plus f3 plus f5 plus f7 plus f8. Could that be a Zeckendorf decomposition?
No, because you're using adjacent Fibonacci number.
Good. So not Zeckendorf. We have adjacent summons. If you go back, could 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, could that be a Zeckendorf decomposition? So if I read this as f1 plus f2 plus f3 plus f5 plus f6 and so on, could this be a Zeckendorf decomposition?
No,
No, why not?
because you're using adjacent summons. I don't know how you're how do you know that it's F1? How do you know you're using adjacent summons though?
Well, I'm just saying, if you want to read this, if you read this so that this corresponds to the first digit, the first index, this corresponds to the second index. Yeah, if we're doing this as powers of 2, it would be 1 plus 2 plus 4. We would have no 8s, we would have a 16, we would have a 32nd, and so on. If I view this as Fibonacci's, we would have trouble. It would not be a Zeckendorf decomposition because we would have two adjacent terms. So there's a lot of similarities between binary decompositions and Zeckendorf decompositions. If I give you, for example, f1 plus f4 plus f7 plus f9, I could write this as I have the first, I don't have the second, I don't have the third, I have the fourth, I don't have the fifth, I don't have the sixth, I have the seventh, I don't have the eighth, I have the ninth. I could maybe do a z down here for Zeckendorf. Oops. That's a 1, not an 8, sorry. So I could view the Zeckendorf decomposition as a string of zeros and ones. And I can interpret this as, this is going to be f1, and here this is f4, and here this is f7, and this is f9. So if I give you a string of zeros and ones, and I view this as a Zeckendorf decomposition, I just take the Fibonacci with the index in the corresponding spot where there's a 1. So if I have a 1 as my units digit, I have f1. If I have 1 as a second digit, I have an f2. So there's a lot of similarities between Zeckendorf decompositions and binary strings. The biggest difference is for Zeckendorf decomposition, I can't have 2 consecutive summons. But for binary decompositions, I can. So this means I don't expect to see the same behavior for gaps for Fibonacci numbers in the Zeckendorf decompositions as I would for gaps of binary decompositions. What's the one gap we're not going to see for Fibonacci's in Zeckendorf decompositions that we could see in binary? So what is a gap that we could see in binary decompositions that we're not going to see in Zeckendorf decompositions between indices? So this has already been said today. What's the gap that emerges that we can see in binary decompositions that we'll never see in a Zeckendorf decomposition?
Well, in Zeckendorf, we'll never see 0 or 1.
Good. So now if we look in binary, we'll never see a 0, right? Because that would mean we would have to have 2 copies of the same thing. But we could see a gap of length 1. So the difference, exactly as you said, is for Zeckendorf decompositions, we'll never have gaps of length 0 or 1. For binary, we'll never have gaps of length 0. So unfortunately, if we analyze binary representations and gaps, it's not going to be exactly the same as the Fibonacci's, but it will be pretty close. And so essentially what we're doing is we're looking at all possible strings of zeros and ones. For binary, we have no restriction on the strings of zeros and ones. For Zeckendorf decompositions, we have the restriction that when we construct our string, we can never have 2 adjacent ones. And so the question is, if I put on additional properties, would you be surprised if there's different behavior? So we have Zec is similar to binary strings of zeros and ones with the extra condition cannot have 2 consecutive ones. As a general rule, if you put on additional constraints, do you expect the subset to have the same behavior or different behavior as the whole system? So for example, if I'm interested in, say, the average math ability of Williams undergraduates, do you think if I sample from my class, say 349 and 383, do you think this would be representative of the average Williams student?
No.
No. If I wanted to understand, say, the typical football ability of Williams students, if I sampled from the football team, do you think that would be a good representative sample?
Also no.
Also no. So if you look at a subset, there's the possibility that you might see different behavior. What if I looked at left-handed versus right-handed? Do you think it would matter if I sample from the math class or from the football class, or do you think that would be similar to Williams as a whole? And that might actually be a loaded question to answer in 21st century America, as to, do certain things correlate, left-handedness, could that mean something about maybe how your brain is developed? What about hair color? The question is, can you find something that really should not be changed depending on what we look at? So maybe month of birth. For football, that actually could depend a little bit, because typically there's some great studies on this. You want to be the oldest kid to just miss the cut, because then you'll be playing in an age group where you're one of the older kids. And when you're very young, typically if you're a few months older, you're a little bit bigger, a little bit stronger, you play a little bit better. So the coaches give you more playing time and more training, and it just propagates upwards. And there's some wonderful articles about how the distribution of births in professional sports are not uniform across the year, like a lot of birthdays, but are actually correlated with the cutoffs of making it into different age groups. But we always want to just ask if we think that this subfamily is generic or if it has some special properties. So let's go back and let's try to analyze binary gaps. So we'll choose, say, some x in 2 to the m, 2 to the m plus 1. So that means we can write x as 1 times 2 to the m plus 1 times, we'll let bk be 2 to the k. So we'll do b to the I2 plus, well, I've got to decide, do I want to have my indices high or low? We'll have them be high. We'll have this be bik minus 1 plus 1 times bik minus 2, all the way down to plus 1 times b1. And so this would just be bik would be 2 to the m. So ik would equal m. So I'm just choosing my numbers so that the first index which happens is the 2 to the m. And here I'm assuming that x has exactly k summons. And so when I write this out, I could even put in a little bit more at the end. So this should be b, let's do I2 plus 1 times b I1. So what's my first gap going to be? So how far is the index I2 from the index I1?
1.
Why 1? That would mean that they would have to be adjacent. So if we go back over here, we would have I1 equals 1, I2 equals 4, I3 equals 7, I4 equals 9. We have 9 summons. The first summoned is 1, the second summoned is 4 as its index, the third summoned is 7, the last one is 9. So in this case, how far is it from index I1 to index I2? Well, let's go back here. How far is it from index I1 to index I2 here?
3.
And the next one?
3 and then 2.
And then 2. So to go from I1 to I2, we got 3. How did you get 3?
By counting the gap.
By counting the gap. So what would it be from I1 to I2? And again, since I'm not telling you I1 and I2, your answer has to be a function of I1 and I2. So what would that gap be?
1 times b of I2 minus 1 times b of I1.
No. If we did b of I2 would be 1, 2. So this would be 1, 2, 4, 8. So if we did b4 minus b1, that would be 7. We're trying to figure out how many indices separate them. How many indices is it from F1 to F4? There's 3 that we're missing. It's a gap of length 3. So over here, when we're going from I1 to I2, how many indices are we missing? How many do we have to add to get from index I1 to index I2? I mean, we've said this before. When we went from I1 to I2, we went from index 1 to index 4, and you said it's a gap of length 3. How do you get 3 as a function of I1 and I2?
You do the value at the value at I2 minus the value at I1.
It's just I2 minus I1. How do we get the next gap? It's just I3 minus I2. So what would be the first gap here?
I2 minus I1.
It's just I2 minus I1.
Can you explain what, I don't understand the notation. Like, what is xg? 2 to the m, 2 to the m plus 1.
That's X is an element of.
Oh, x is an element of, okay.
So we're choosing some X between 2 to the m and 2 to the m plus 1. So we write it in binary. Because it's in this interval, it has to have 2 to the m as one of its summons. So let's assume for definiteness that it has k summons. So I know I have k powers of 2 that occur. I'll call the largest one ik, I'll call the smallest one I1. And so I know ik has to be m. I don't know where ik minus 1 is. I don't know where the next one is. That's why I can't just write b8, b7, b6, because I don't know that my first summon is b8, my second summon is b7. I have to just say it's some general number. And so in this case over here, when I had 1, 0, 1, 0, 0, 1, 0, 0, 1, I had, I'm doing things here with Fibonacci's, but I could, of course, just consider this as a base 2. I have the first one, I don't have the second, I don't have the third, I have the fourth, I don't have the fifth, I don't have the sixth, I have the seventh, I don't have the eighth, I have the ninth. So the indices in play would be I4 would be 9, I3 would be 7, I2 would be 4, I1 would be 1. Because I have 4 summons, my k would be 4. The largest one would be 9, that's why I4 would be 9. The smallest would be 1, that's why I1 would be 1. And I want to just see how far do I have to go from one index to the next index that occurs. And that would just be the difference. So that would just be I2 minus I1. If things don't make sense, this is the time to speak up before we continue. I want to make sure everybody follows what we're studying and how we're calculating these gaps. We're just trying to see how long do we have to wait from one index that's in the decomposition to the next index in the decomposition.
I understand this slide. The next slide is where I start to not understand.
Okay, so I'm now just writing X in binary. I just have some summons. I don't know which ones I have. That's why I can't write down the index. I have to use notation. I1 is the first index that we have. It's the smallest. I2 is the second smallest. IK is the largest. I'm assuming X has K summons just so I can write things down. K could be 1, it could be 2, it could be M. So for example, if I give you, 187, I could write this as 128, and then I would have to add what? 59? Yes? Correct, yes?
Yeah.
Which is 128 and 59. I can write that as 32. And then to get to 59, I would have to add 27.
Yeah.
So 128 plus 32, 27 I can write as 16 plus 9. So it's 128 plus 32 plus 16, and the 9 is 8 plus 1. So if I want to write this in binary, I have 1, I don't have 2, I don't have 4, I have 8, I have 16, I have 32, I don't have 64, I have 128. So this would be 1, 2, 3, 4, 5, 6. This would be B8 plus B6 plus B5 plus B4 plus, I put the other here, plus B1. Okay. But now let's write this in terms of summons. How many summons do I have here? How many summons are there? It's B8 plus B6 plus B5 plus B4 plus B1. How many summons are there?
5,
5. So what would the value of K be?
5,
5. So we would have this as BI5 plus BI4 plus dot 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 plus BI1. And here, what would I1 equal? It would be 1. What would I2 equal?
Why are you adding? So I get that there's 5 now because the 8, 6, 5, 4, 1. So there's 5. K is 5.
Yep.
Why are you now adding BI5 plus BI4 all the way to BI1?
Well, I'm just trying to write this in general notation. And so I have 5 summons, right?
So is BI5 synonymous with B8?
Yes, because I5 equals 8. So what would I2 equal?
4.
I2 would equal 4. What would I5 equal? I mean, I'm sorry, I3 equal. That'd be 5. What would I4 equal?
6, and then
6.
I5 is 8.
Right. So if I want to write it as the sum of terms, as the sum of powers of 2, I can do that. What I'm trying to do is I'm trying to write x as the sum, let's say L goes from 0 to n of epsilon L 2 to the L, where epsilon L equals 0 or 1. I don't know initially which epsilons are zeros or ones. I'm trying to just isolate which of the epsilons happen to be ones. And so let's imagine, epsilon 1, epsilon 4, epsilon 5, epsilon 6, epsilon 8 equal 1, and the rest are 0. I could write this as 1 times 2 to the 8 plus 0 times 2 to the 7 plus 1 times 2 to the 6th plus 1 times 2 to the 5th plus 1 times 2 to the 4th plus 0 times 2 cubed plus 0 times 2 squared plus 0 times 2 plus 1 times 1. Or I could just write it as 1 times 2 to the 8 plus 1 times 2 to the 6th plus 1 times 2 to the 5th plus 1 times 2 to the 4th plus 1 times 1. Just writing down the terms that aren't 0. And so this would be my I1. This would be my I2. This would be my I3. This would be my I4. And this would be my I5. So it's just which indices are not 0. But the problem is until I give you my number, I don't know what it's going to be. So I just have to write x is, the sum of b I sub k. Or so b, let's say b sub I sub L. L goes from 0 to k. I don't know which terms happen to be non-zero. I just know that there's k terms. I don't know, is the first one used? Is the second one used? Is the third one used? But I really want to make sure everybody understands this, because if we don't understand these decompositions, then we can't study the gaps between them. So I want to make sure by the end of today, everybody understands how we decompose the numbers and how we talk about the gaps.
When you write I5, are you writing I sub 5 or just the 5th? Like it's sub, right?
What I'm writing, I'll write it very large. We have b sub I sub 5. We have b sub I sub 4. B sub I sub 3. So this whole thing, it's the index. We don't know which terms are used. That's why we have to, we can't just write B5, B4, B3, because we don't know if we have the 5th term. We don't know if we have the 4th term. that's why we just have some general sequence. We have, I1, I2, I3, I4, I5. These are my 5 indices in play for something with 5 summons. And then it turns out that I1 is 1, I2 is 4, I3 is 5, I4 is 6, I5 is 8 for this specific example. But if I give you a different number that has exactly 5 summons, for example, if I gave you, let's say I gave you 1, 1, 0, 0, 0, 0, 1. Oh, that's too many zeros. Let's say I gave you this. Now for this one, we would have, this would be 2 to the 8 plus 2 to the 7, 2 to the 5th, 2 to the 1st, 2 to the 0. So now for this one, what would I1 equal? What would I2 equal? What would I3 equal? So what would I1 equal?
One.
Right. Wait, did I shift things off by 1? Okay, sorry. I just realized, I do apologize. I should really be calling this I1 equals 0. I'm sorry, this is really the 0th summoned. So let me just quickly fix that. So over here, so I think everything gets shifted down by 1. This is the difference between Zeckendorf decompositions and binary. I apologize. In binary, we start counting at 0. In Zeckendorf, we start counting at 1. So I apologize for that. View all of these as Zeckendorf. So if we do it like that, yeah, this really, we should shift everything by 1. So I'll shift everything down by 1. So it should be 0, 3, 4, 5, 7. And I1 would be 0. What would I2 be? That'd be 1. What would I3 be?
5.
5, 7, 8. So this would be another number that has 5 indices, but they would have different values. So over here, these should all be shifted down. So that should be 0, that should be 3, that should be 4. Oh no, I'm sorry. The way I'm doing it here, the only one that needs to be fixed is the last one. Is that should be 0. Everything else was fine. Over here, if I'm doing things with binary, all of these should be shifted down by 1. And so instead of 1, 4, 5, 6, 8, it should be 0, 3, 4, 5, 7. Does this make sense in terms of how we get the decompositions?
It did until we started changing the things.
Well, it just, are we starting to count at 0 or are we starting to count at 1?
So
When we do-
binary, you count at 0. Binary,
Right,
you count at
because we
0.
start off with 2 to the 0. So the first index is the 0th index. When
So
we do Zeckendorf, the first index is 1.
Okay.
So the main thing is just if I give you anything, if people have to leave, that's fine. If I give you 1, 1, 0, 0, 0, 1, 1, 0, 1 in binary, this would mean we would have I1 is 0. And I2 would then be 0, 1 would be 2. I3 would be 3. And the first gap would be over here, would be a gap of length 2, and then a gap of length 1.
Professor Miller, we're out.
Yep.
I have to run.
Yep. All right. If people have questions about this, send me an email and we can talk about this further. But I want to make sure everybody understands this for the next class. All right. Have a